Membrane potentials. Resting membrane potential. If two electrodes are placed on the cell surface, no potential is recorded. On the other hand, if a reference electrode is placed on the cell surface, and a recording electrode is placed inside the cell, a negative gradient of 60 to 90 mV is recorded, the intracellular medium being negative relative to the extracellular medium. This gradient is called the resting membrane potential. The resting membrane potential is very negative, because potassium channels are open, and potassium outward current is high. The positive potassium ions are leaving the cell, and thereby making the membrane potential more negative inside. At the same time, sodium and calcium channels are closed. What is the meaning of a negative gradient? The negative sign, minus, is used just to indicate that the intracellular potential is lower than the outside potential. It does not at all indicate a mathematical value. Thus, a gradient of minus 90 mV, for example, is higher than a gradient of minus 70 mV, which means that the difference is bigger in absolute figures, although mathematically minus 70 is bigger in value. Threshold potential. For the cell to be excited, the resting membrane potential must decrease, to become less negative, to a certain potential called the threshold potential, usually minus 50 to 70 mV. This means that reducing the resting membrane potential augments excitability. Action potential. This is the potential fired by the cell when excited. The action potential occurs due to changes in electrolyte currents, including sodium, potassium, and calcium currents. It represents two events, depolarization and repolarization. This figure illustrates that the action potential is fired when the resting membrane potential decreases, becomes less negative, until it reaches the threshold potential. Potentials more negative than the resting potential are called hyperpolarization. Two types of action potential are identified: fast response type, occurring in non-pacemaker cells when excited by an external stimulus, and slow type occurring automatically in pacemaker cells. The fast type occurs when the resting membrane potential is relatively more negative, and sodium channels are more active. Phase 0 is triggered by sodium channels. The slow type occurs when the resting membrane potential is relatively less negative, and sodium channels are less active. Phase 0 is thought to be triggered by calcium channels. Non-pacemaker action potential. The action potential recorded on depolarization of non-pacemaker cells, atrial and ventricular myocytes, is very rapid, fast response action potential. It consists of 5 phases. Phase 0, representing depolarization, or better called reversal of polarity. And phases 1, 2, and 3, representing repolarization, or return to the resting state. And finally phase 4, which is also called the resting membrane potential. Non-pacemaker action potential, phase 0. Phase 0 is the rapid depolarization phase. It is fired when the non-pacemaker cells are rapidly depolarized to a special potential called the threshold, about minus 70 mV. This phase is mediated by opening of sodium channels, generating a transient sodium inward current. At the same time, potassium channels close. Non-pacemaker action potential, phase 1. Phase 1 represents initial rapid repolarization, mediated by opening of potassium channels, generating an outward potassium current. Non-pacemaker action potential, phase 2. In phase 2, plateau phase, there is a balance between the outward potassium current and an inward calcium current, through the long-lasting, L-type, calcium channels. This phase prolongs the action potential duration, unlike the situation in nerves and skeletal muscles. This explains why the cardiac muscle cannot be tetanized, unlike other muscles in the body. Non-pacemaker action potential, phase 3. Repolarization phase 3 occurs when the potassium current overcomes the calcium current. Non-pacemaker potential phase 4. This is the resting membrane potential mediated by sodium-potassium equilibrium currents. This figure illustrates phases of the action potential in non-pacemaker cells. Phase 0, mediated by sodium inward current. Phase 1, mediated by potassium outward current. Phase 2, representing a balance between potassium outward and calcium inward currents. Phase 3, mediated by potassium current overcoming calcium current. And Phase 4, the resting potential, mediated by sodium-potassium currents equilibrium. To conclude, with dominant sodium and/or calcium inward currents, and low potassium outward current, the membrane potential is more positive, phases 0, 1, and 2. On the other hand, with high potassium outward current and low sodium and calcium inward currents, the membrane potential is more negative, phases 3 and 4. Effects of antiarrhythmic drugs. Class 1, the sodium channel blockers, decrease the slope of phase 0 of the action potential. They are further subdivided into subclass 1A, which prolong the action potential duration, subclass 1B, which shorten the duration, and subclass 1C, which do not affect the action potential duration, as illustrated in these figures. Class 2 includes the beta-adrenergic blockers, which decrease phase 4 slope. Phase 4 slope is known to be augmented by beta-sympathetic stimulation. In this way, beta-adrenergic blockers decrease the pacemaker firing rate, decrease the conduction velocity, and prolong the action potential duration and the refractory periods. This figure demonstrates that sympathetic stimulation augments phase 4 slope, shown in orange, while vagal stimulation reduces phase 4 slope, shown in blue, relative to the normal slope, shown in black. Class 3 includes the potassium channel blockers, which delay the plateau phase and the repolarization phase 3, thus prolonging the action potential duration, as illustrated in this figure. Class 4 includes the calcium channel blockers, which reduce the slope of phase 4, and the slope of phase 0 as well. Refractory periods. Absolute refractory period comprises phases 0, 1, 2, and part of phase 3 of the action potential, during which there is absolute refractoriness, so that the tissue does not respond to any stimulus, whatever strong it may be, thus a new action potential can never be initiated. Relative refractory period comprises the rest of phase 3, during which there is relative refractoriness, so that the tissue responds only to extra strong stimuli. Effective refractory period. This is the summation of absolute refractory period, plus part of the relative refractory period, during which no new action can be generated. Its length depends on the circumstances, and the strength of the impulse at a given moment. The effective refractory period is a protective mechanism, preventing repetitive action potentials, thus preventing tetany of the heart muscle. Remember, the heart muscle cannot be tetanized. This figure illustrates the effective refractory period, which is the summation of the absolute refractory period, plus part of the relative refractory period, during which no new action potential can be generated. Its length depends on the circumstances, and the strength of the impulse at a given moment. Phases of excitability. The phases of excitability, responsiveness of the tissue to stimuli, can be concluded from the above discussion as follows. Absolute refractoriness, no response, phases 0, 1, 2, and part of phase 3 of the action potential. Relative refractoriness, response only to extra strong stimuli, last part of phase 3. Supernormal excitability, before returning to normal excitability, a very short period of hyperpolarization occurs, at the start of phase 4, causing supernormal excitability, wherein a weak stimulus may fire a new action potential. Normal excitability, most of phase 4. The surface electrocardiogram, ECG. Phases 0, 1, 2, and 3 of the action potential, generate small voltages which can be detected by electrodes attached to the skin. The ECG signal reflects the summation of innumerable tiny currents, from billions of cardiac cells, which is proportional to the muscle mass. Phase 4, the resting membrane potential, on the other hand, produces no measurable electrical effect at the surface of the body. Phases 0 and 1 of the action potential correspond to the QRS complex. Phase 2 to the ST segment. Phase 3 to the T wave. and phase 4 to the TP segment. Resting membrane potential and action potential in pacemaker cells. The potential in pacemaker cells, primarily the sinoatrial and the atrioventricular nodes, differ from those in non-pacemaker cells in the following features. Phase 0 has a slow rise with low rounded peak. Unlike phase 0 in non-pacemaker cells, it is largely dependent on the slow inward L-type calcium current, not the sodium current. Repolarization is only a single phase. The resting membrane potential, phase 4, is less negative, about -60 mV, instead of about -90 in non-pacemaker cells. In pacemaker cells, phase 4 has another very characteristic feature, which is the occurrence of spontaneous diastolic depolarization, where the resting membrane potential decreases spontaneously, becomes less negative, gradually, until it reaches the threshold potential, about -50 mV. A new action potential is then automatically fired, without the need for external stimuli. That is why the pacemaker cells are called automatic. In pacemaker cells, phase 0 has a slow rise with low rounded peak, repolarization is only a single phase, and the resting membrane potential, phase 4, is less negative than in non-pacemaker cells. Mechanism of spontaneous diastolic depolarization. Spontaneous diastolic depolarization results from an inward current, called the funny current, mediated mainly by sodium, but other currents may be operative, including the potassium current, the transient T-type calcium current, and the long-lasting L-type calcium current. Ivabradine reduces the sinus node rate by reducing the slope of spontaneous diastolic depolarization in phase 4 of the action potential. Thank you.